We like to start here very often. I don't know whether to reassure you or to disconcert you, but this is one of the most popular sayings about quantum mechanics from Richard Feynman, who said, "I think I can safely say that nobody understands quantum mechanics." Now, he said this in 1965, and that was the year that he shared the Nobel Prize in Physics for his work on quantum mechanics. So at that point, no one alive knew more than Richard Feynman about quantum mechanics. What hope is there then for the rest of us? Well, quantum mechanics has this reputation for being impossibly hard, but it's not the mathematics that's the problem. And here's some of the mathematics, and it doesn't look particularly easy to grasp, but actually Feynman was fine with it. He could do the mathematics just fine. The trouble was, that's all he could do. What he couldn't understand is what the maths meant, what it tells us about the nature of the world. And Feynman himself didn't seem too troubled by that. He said, well, we've got a theory that works. It makes amazingly accurate predictions about how stuff will behave. What more do you want from a theory than that? Some scientists feel that same way today, but usually we do want more. We want to know what scientific theories tell us about what the world is like. And it wasn't clear then quite what quantum mechanics was telling us about what the world was like, and it's still not clear now. But I want to suggest that we can do better than Feynman's admission of bafflement or defeat, some might say. We don't have all the answers about what quantum mechanics means, but we do have better questions. We have a clearer sense than we did in the 1960s, or even in the 1980s, of what's important and what isn't. And I want to try to give you some sense of what I think that is. And let me start with some of the things that everyone knows about quantum mechanics. And when I say everyone, I mean everyone in inverted commas. So if you haven't seen these things before, don't worry. All I mean is that once you start finding out more about this problem, perhaps this topic, perhaps by reading popular accounts of it, then pretty soon these are notions that you will encounter. And the first of them is that quantum mechanics is weird. And I want to show you what some of those weirdnesses are. The first one is that quantum objects can be both waves and particles. And this is called wave-particle duality. The second is that quantum objects can be in more than one state at once, or more than one place at once. They can be both here and there, and these are known as quantum superpositions. Then we hear that you can't simultaneously know exactly two properties of a quantum object, and this is Heisenberg's uncertainty principle. Quantum objects can affect each other instantly over huge distances. This is so-called spooky action at a distance, and we'll hear more about it shortly. And it arises from a phenomenon called entanglement. You can't measure anything without disturbing it. And so the human observer can't be extracted from the theory. It becomes unavoidably subjective. And then everything that can possibly happen does happen. And there are two reasons why this is often said. One of them comes from Feynman's work itself, which seems to say that quantum paths take all possible routes through space. The other comes from the controversial many worlds interpretation of quantum mechanics, which says that every time a quantum system faces a choice of what to do, it takes both choices. Okay, now here's the thing. Quantum mechanics says none of these things. They're attempts to explain or to articulate what quantum mechanics means. Some of them are misleading. Others, I think, are just plain wrong. Others are just unproven interpretations or assumptions. I'm saying that we need to change the record when we talk about quantum mechanics. We need to stop falling back on these tired old cliches and metaphors and look more closely at what quantum mechanics does and doesn't permit us to say. And the first point to realize is that there's a big difference between quantum theory, the mathematics and the mechanics that you just glimpsed, which scientists use daily to make predictions, to predict stuff that allows them to build things like this laptop. So this is stuff that really works. There's a big difference between that and the interpretation of the theory. And this is what's so hard to grasp about quantum mechanics. Because normally, the interpretation of a theory is kind of obvious. Newtonian mechanics, this is the old classical mechanics that tells us how everyday objects move about and behave. So it tells us how things like tennis balls and spaceships move. The interpretation here isn't difficult. The Newtonian mechanics tells us what paths objects take through space as forces act on them. And we don't have to ask, what do you mean by path? What do you mean by object? What do you mean by force? It's kind of obvious. Well, that's not so for quantum mechanics. And let me give you a glimpse of why. To predict what a quantum object will do, in place of Newton's equations of motion, scientists generally use the equation devised by Erwin Schrödinger in 1925 to describe the idea that quantum particles might act as if they were waves. This is the Schrödinger equation, and it doesn't tell us what the trajectory of a particle is. Instead, it gives us something called a wave function. And the wave function can be used to figure out where we might find an object and what properties it might have, an object like an electron, say. So the typical shape of a wave function of a particle like an electron in space might look something like this. Okay, so what does this mean? Well, it's often said what it means is that the particle is somehow smeared out over space. And it does kind of look that way, doesn't it? But this isn't showing the density of the particle over space. This wave function is a purely mathematical thing. And what the wave function lets us deduce is all the possible outcomes of measurements that we might make on the particle's properties, such as its position, along with the relative probability that we'll get that particular result when we make the measurement. So to find out the position where we would observe this particle, we simply calculate some number from the wave function, the value of the wave function, at that point in space. And that gives us the probability that we'll see the particle there if we make a measurement. So the wave function doesn't tell us where we'll find this particle. It tells us the chance that we might find it at a particular position if we look. And this is what's so odd about quantum mechanics, because it seems to point in the wrong direction, not down towards the thing that we're supposed to be studying, but up towards our experience of it. It says nothing, or perhaps we should say it says nothing obvious about what the quantum system itself is like. In other words, the wave function is not a description of the quantum object. It's a prescription for what to expect when we make measurements on the object. But it's even more peculiar than that, because the wave function doesn't tell us where the particle is likely to be at any instant, which we can then try to verify by looking. Rather, what the wave function tells us, well, it tells us nothing about where the particle is until we make a measurement. Strictly speaking, we shouldn't talk about where the particle is at all. We shouldn't talk about a particle at all, except in terms of the measurements that we make on it. Now, this account of quantum mechanics is more or less the one given by the Danish physicist Niels Bohr and his collaborators, such as Heisenberg, and it's known today as the Copenhagen interpretation. Copenhagen was where Niels Bohr was based. Now, I'm not saying that this interpretation is the right one, but what's valuable, I think, about it is that it tells us where our confidence about meaning has to stop. As it stands, quantum mechanics doesn't permit us to say anything with confidence about reality beyond what we can measure of it. And here's what I mean by that. One way of speaking about this measurement of a quantum particle says that before the measurement, the wave function might be this typical sort of broad, spread out thing. But when we make a measurement on the particle, suddenly it collapses into this spike at one particular place because we know, having made the measurement, where the particle is. Now, this is generally called, for obvious reasons, collapse of the wave function. And the problem is that there's no real physical prescription for what's going on here within quantum theory. You have to sort of put in this collapse by hand. So that's a problem. But wave function collapse doesn't mean that the particle goes from being sort of smeared out before we make a measurement to being sharply defined when we make it. All it says is that before we make the measurement, there were various different probabilities that a measurement might reveal it at particular places, whereas after the measurement, we know for sure that it's there. What's changed is our knowledge. And some researchers think that this is really what quantum mechanics is, that it's a theory describing how our knowledge of the world changes when we intervene in it. And we can't deduce anything from that about what the world was really like before we had that knowledge about it. So you see, it's misleading to talk in this situation about the particle being in many places at once. The situation tells us only about the possible outcomes of measurements. It's the same thing, the same story, with this notion of quantum superpositions. And now, it's often said that the odd thing about quantum mechanics is not just that they can be in two places at once, but they can be in two states at once. And I want to illustrate what that means by referring to a property that quantum particles have called spin. And you don't need to know anything about exactly what this means, except that for some particles, for an electron, say, the spin can have two values, and you could think of them as spin being up or spin being down. And if you make a measurement on the particle, on the electron, then you'll find one or the other. So it's a binary property, really. And for that reason, spins like this can be used to encode binary information. So you could say the spin up is a 1 and the spin down is a 0. And that's the basis of the quantum information technologies that we're starting to hear about, like quantum computers, in which spins or other quantum states act as quantum bits, or qubits as they're called. But spins can be not just up or down, a qubit of 1 or a 0, they can be in a superposition of up and down states. So what does that mean? Well, it's often said that what it means is that the particle, the electron, is both up and down at once at the same time. But that's not right. Remember that the wave function tells us only what to expect when we make a measurement. And so in this case, what it's saying is that in a superposition state, a measurement might give us an up or a down spin. And in fact, those are the only possible outcomes of a measurement. But what's the qubit like before we make that measurement, when it's in this superposition? Quantum mechanics doesn't really tell us that. Well, you see, now I'm not talking any longer about smeared out particles or collapsing waves, but about information, and how information can be encoded in quantum systems and how we can read it out by making measurements. This is the perspective that's offered by so-called quantum information theory, which is not just a basis for making these amazing quantum technologies like quantum computers or quantum cryptography, which is a way of encrypting information that it's impossible to tamper with, to eavesdrop on without being detected. It's not just that, it's really also a new way of talking about quantum mechanics itself. Talking about quantum mechanics as in terms of information, allows us to see past all the old-style paraphernalia of wave functions and Schrödinger equations and quantum jumps, and I think to get closer to the core of what the theory seems to be telling us. And I want to tell you a story about that, and I've got some props here to help me. Now, I hope it will be illuminating, but at the very least, I'm fairly sure that it's the first time that you will have seen quantum mechanics discussed with the help of Sylvanians. Here they are. So I have two boxes here, A and B. One belongs to Alice, one belongs to Bob, and I'll leave you to figure out which is which. And they are boxes in which they produce one of these cute toys, either a rabbit or a dog, when we put coins in. And they will take either a £2 coin or a £1 coin. So we put a coin in, and we get one of these toys out. And there are rules how that works. And I'm just going to stipulate what some of the rules are that these boxes are going to work by. First of all, here's the boxes. So this is what's going on. And I'm going to say, first of all, that rule number one, if Alice puts a £1 coin into her box, it'll produce a rabbit. Okay. Now I'm going to add two other rules. If Alice and Bob both put in £2 coins, then the boxes between them will deliver one rabbit and one dog. It doesn't specify which way round that would be, but we'll just get that combination. Any other combination of coins than both putting in £2 will produce either 2 rabbits or 2 dogs. I'm just stipulating these rules. Now I want to find out, what do the inputs and outputs have to be in order to satisfy them? A pound in Alice's produces a rabbit. Okay, a pound in Bob's produces what? Well, let's think about that. In fact, we kind of have a lot of these answers already. So we already know, okay, a pound in Alice's box produces a rabbit. Okay, well, when you think about it, that means that whatever Bob puts in, a pound or a £2, has to produce a rabbit, because it could only produce a dog in the case where both put in £2. That's one of our rules. That's the second rule. So we've almost got all the rules already. All we need to know now is what happens when Alice puts in £2. Okay, well, we know that if Alice puts in £2 and Bob puts in if Alice puts in £2 and Bob puts in £2, we know we have to get a dog and a rabbit. Okay, that's our third rule. So that means if Alice puts in £2, Bob puts in £2, we get a dog. But that means also that we get a dog in this case as well. Alice puts in £2, it gives you a dog. Okay, the trouble here is that this doesn't work, because we're not meant to get a dog and a rabbit in this top case, only in the bottom case where they both put in £2. So that one is wrong. Now, what it means is we can only satisfy those rules 3 times out of 4. We get 75% success rate. Maybe we can do better. Well, no matter how you try and juggle it to see if there are any other combination that works, you'll find it won't. This is the best you can do. You can only satisfy these rules 3 times out of 4. Okay, but what if Alice's and Bob's boxes could switch their output depending on what the other one put in? Then it's a different matter. Then we could say maybe Alice's box gives a dog when Bob puts in £2, but a rabbit when Bob puts in £1. Okay, well, that might work. The thing is, then we have to know what one has put in before the other box decides what it's going to give out. So we need to have some communication between the boxes. So we need to wire them together, and they'll send a signal between them, and then we can do better. Well, okay, that's fine, but this signal has to travel down the wire, and it can only do that at the speed of light. That's fine if they're here. That takes, no time at all, virtually, but it takes some time. And in fact, even at the speed of light, if Alice's box is here and Bob's box is in, let's say, Fiji on the other side of the world, it takes 1/10 of a second for the signal to travel there. So we have to wait that long before Bob puts in his coin, or before Alice puts in her coin, whichever way around we do it. So we can't do any better than this instantaneously, if Bob and Alice put in their coins instantaneously. So we're kind of stuck. This communication won't work if we're looking at how to solve this problem instantaneously. However, these are classical boxes. Now, what happens if they're quantum boxes? Well, then we can do better, because it turns out that the rules of quantum mechanics permit us what looks like a kind of communication between the boxes that happens instantly, and which would allow the boxes to share some information between them without any physical connection between them. I'm going to say some more about this quantum effect that allows us to do this. Just take my word for it at the moment that quantum mechanics allows us to do it. Well, then we can do better. Then what Bob puts into his box can instantaneously seem to affect what Alice puts into her box, and then we can do better. So does that mean then that we can satisfy these rules all the time? Well, actually, we can calculate using quantum mechanics how well we can do in that case. And it turns out that if they're quantum boxes, we can't quite get 100% success rate. We can get not precisely, roughly 85% success rate using this quantum, what seems like communication between the boxes. Now, what I've just told you about, this mysterious quantum link, is the quantum phenomenon called entanglement. And I wanted to do that without any maths, without any Schrödinger equation and wave-particle duality, even without any particles, just with Sylvanians. Okay. Hang on, though. What's going on here? Because doesn't Einstein's theory of special relativity say you can't send any signals faster than light? The speed of light is the ultimate cosmic time speed limit. Well, that's true. But you see, what's going on here is that Alice and Bob can't actually verify that they've got this 85% success rate without swapping information about what their boxes produced. And the only way they can do that is by communicating with each other in some normal way, by email, by carrier pigeon, by letter, whatever. Well, however they do it, they can't do it faster than light. And it turns out that actually this is what special relativity forbids. That you can't verify that you've got this success rate faster than light. And what that effectively means is that Alice and Bob can't use this quantum entanglement to send any information to each other faster than light. And that, it turns out, is fine with special relativity. Well, entanglement was discovered in 1935 by Albert Einstein and by two younger colleagues called Boris Podolsky and Nathan Rosen, who were perhaps ironically trying to show that quantum mechanics, in their view, had a shortcoming. And so Einstein, Podolsky, and Rosen came up with a thought experiment that they believed revealed a deep paradox at the heart of quantum theory, and which could only be resolved by adding something more to it. And this thought experiment was later put in a slightly clearer form by the physicist David Bohm, and that's the form I'm going to talk about now. And what Bohm envisaged was something like this. You have a box that spits out two particles in opposite directions, and they are entangled together. The way they're produced means that they're entangled. And what that means is that there's some relation between the properties of one and the properties of other. And let's think about it in terms of spins. So you can entangle them in such a way that if the spin of one of these particles is up, the other one has to be down. Okay. And then, if we make a measurement on one of them and we see it has a spin up, we know that the other one will have a spin down. So they're correlated. Now, perhaps you can see that this is a little bit like these two boxes here, but in the sense that the measurement here is playing the same role as me putting coins in, and what we see, spin up or spin down, is a binary choice, just like getting a rabbit and a dog. So this was really an entanglement experiment. Now, actually, this correlation might sound unremarkable to you, because you might say, well, we could do this with a pair of gloves, let's say, a left-handed glove and a right-handed glove. And we could send one to Alice in Melbourne or something and one to Bob, in Shepherd's Bush. And then as soon as Bob opens his parcel and sees that he's got a left-handed glove, he knows instantly that Alice has got a right-handed glove. Instantly, he knows that must be true because they started off as a pair. So what's the big deal? Well, here's the big deal. According to the Copenhagen interpretation, the direction of these spins, up or down, for these two entangled particles, unlike the handedness of those two gloves, isn't actually determined until we observe them, until we make a measurement. And if that's so, then this experiment by Einstein, Podolsky, and Rosen seem to be saying that making a measurement on one particle somehow instantly fixes the other, as if the result of that measurement is being spookily communicated to the other particle instantly. This is what Einstein called spooky action at a distance. And again, he said it can't be right because special relativity seems to forbid it. Well, for a long time, no one knew quite how to sort of resolve this paradox, what the flaw in the reasoning or what the problem was, or maybe Einstein and Podolsky and Rosen were right. No one knew what to do with it, and it was brushed under the carpet. That changed in 1964 when an Irish physicist named John Bell, whose day job, sort of like John's, I guess, was a particle physicist at CERN in Geneva. But in his spare time, he turned quantum mechanics on its head, and he reformulated the Einstein-Podolsky-Rosen experiment in a way that showed how you could make a measurement to try to figure out what was going on here. And in fact, what he's drawn on the blackboard there is basically a diagram of the experiment that he thought of. And this experiment, this procedure, it's kind of slightly analogous to these black boxes here, because what John Bell basically showed was that if you make some measurements and you find that there's a certain amount of correlation, in fact, in his case, again, 75% correlation, so you know the rules seem to be obeyed 75% of the time, then it shows that you've got something like classical physics, or in fact something like what Einstein, Podolsky, and Rosen thought was going on, which was basically saying those spins must have been fixed all along somehow by some variable that is hidden, that we can't see and can't measure, okay? But if you get a better correlation than that between the two spins, if you get this 85% that quantum mechanics predicts, then Einstein's picture doesn't hold. Quantum mechanics must be right. You must get this strange, what looks like communication. Well, these experiments were done. They were first done in the 1970s. They were first done kind of more rigorously in the 1980s. They've been done countless times since. Every time they've shown the same clear result that quantum mechanics is right. You get a better correlation than any kind of classical physics or any kind of Einstein-like hidden variables picture can give you. So, entanglement really happens. But what was wrong then with Einstein's reasoning in this experiment? Well, he made the perfectly reasonable assumption, so reasonable we didn't even realize it was an assumption, that we can call locality, that the idea that the properties of a particle, of an object, are located on that object. I mean, it just stands to reason. This box's blackness is in the box. What would it possibly mean to say this box's blackness is also kind of partly in this box? But in quantum mechanics, we do seem to have to say things like that. It seems that properties of objects, of quantum objects, when they're entangled, can be non-local. And it's only if we make an assumption that this assumption of locality, that everything to do with this object is fixed here in this location, it's only in that assumption that we have to start thinking about spooky action at a distance and this kind of affecting this instantly through space. What quantum mechanics really tells us is that there's something else, this thing that is just vaguely called quantum non-locality, which means that there's a kind of mixing of these two things that is very hard to put into words, but it means that there's a non-local influence that means, in effect, we can no longer think of these two boxes as separate objects. That's what entanglement means. They've somehow become part of the same quantum entity. So quantum non-locality isn't spooky action at a distance, it's the alternative to spooky action at a distance. Now, Erwin Schrödinger, when he saw what Einstein, Podolsky, and Rosen had said, he recognized that this phenomenon of entanglement actually was pretty central to what quantum mechanics was really about. And in fact, entanglement is what happens all the time when any quantum particle interacts with any other. They have to become entangled. That is the only thing that can happen, according to quantum physics. And what this means is that as a quantum object starts to interact with its environment, its quantumness, you could say, or you could say if it's in a superposition, its superposition starts to spread into the environment. And it becomes harder to see that quantumness, that superposition, in the original object itself. It's sort of spread out, like an ink drop spreading in water. And so what that effectively means is that the quantumness starts to get washed away. This entanglement leads to a loss. Technically, the word is a decoherence of quantum properties, and it seems to be that ultimately leads to quantum objects behaving like classical objects as they start to interact with their environment. So what that's really telling us, and what we can now say, is that there isn't some strange situation in which little things like atoms obey quantum rules, and then for some reason big things like us obey classical rules, and they're just different things. Actually, we can now say that this is what quantum mechanics looks like when you're 6 feet tall. The weirdness that we talk about in quantum mechanics is just the way the world works. And in fact, it's kind of us that are weird, because by the time quantum mechanics has become this scale, it kind of looks different to how it does when you're talking about photons and electrons. Why, though, does quantum mechanics only allow us 85% success? Why doesn't it allow us 100%? Well, it turns out that the answer really is about how efficiently these boxes can share that information about, in this case, what coin was put into them. It's about the efficiency of information sharing. If we can make use of quantum entanglement, then we can improve the efficiency with which information is shared between quantum objects, like qubits. And this is really how quantum computing gets its power, by more efficiently sharing the information among the different bits of the system than we can use when we're using classical bits, like the little transistors in laptops. And what it also tells us is that what makes quantum mechanics quantum, at root, doesn't really have anything to do with notions of wave functions and collapse and wave-particle duality. It's really about what can and can't be done with information. Let me give you a sense of where that's leading us, because it's meant that some researchers feel that we might be able to reconstruct quantum mechanics from scratch, getting rid of things like the Schrödinger equation and waves and particles, but just using some simple axioms about what is and what isn't permitted with information, how it can be encoded and transferred and shared and read out. And I want to give you just a flavor of one of these, what are now called quantum reconstructions. This is one, there are many, this is one suggested in 2009 by Borjove Dekic and Kaslav Bruckner at the University of Vienna. And they proposed 3, what they said were reasonable axioms from which we might try and construct quantum mechanics. And here they are. And they probably don't look that reasonable or even that necessarily intelligible to you, but I'll just briefly say what they mean. Information capacity was the first one. They said, let's assume that all the stuff, all the basic entities, whatever they are, that make up the world, can encode just one bit of information. They're like those spins. They can just be up or down, and that's it. That's all they can hold. Let's also assume, now they call this assumption locality. It's a bit confusing because I've just told you about quantum non-locality, but the locality in this case means kind of something a bit different. All it really means is that there's nothing hidden behind the scenes that's allowing stuff to be done with information. There's no secret device underneath here that's allowing these boxes to communicate. And lastly, this idea of reversibility. They said, let's assume that these bits that can hold just one bit of information, they can be converted reversibly. You can go from a 1 to a 0, from a spin up to a spin down and back again. Okay. They said, and they showed that with just these 3 rules about what can be done with information, you get 2 possible types of physics out of them. One is classical physics and one is quantum physics. With just these rules. What's more, if you tweak this 3rd axiom a little bit to say that, let's assume that in order to do this reversible sort of flipping of spins, that let's assume that you can do it continuously. You can continuously sort of rotate a spin up to a spin down. Okay, if you assume that, you get quantum rules. If you assume it has to be just one or the other without this sort of continuous rotation. So like flipping a coin, heads or tails. Once it's down there, it's got to be heads or tails, and you can't sort of interconvert them. Then you get classical rules. Well, I find that kind of extraordinary. You can get so much out of what seems like so little. And the point about these axioms, about information, is that they can, by themselves, lead to what looks like quantum behavior and all the stuff that we get out of quantum mechanics, like superpositions and entanglement. And some researchers think that these reconstructions might lead us to a completely different perspective on quantum theory, perhaps one in which the physical meaning of all this seemingly strange behavior is clear. Well, that remains to be seen, but what's already illuminating is how they focus on this question of information, on how answers or measurement outcomes are contingent on the questions we ask, just as the outcome of these boxes, what comes out of these boxes, is contingent on what we put in, a £1 or a £2. And I think this is the most productive way to think about quantum mechanics. And there's a very nice metaphor for this perspective that was suggested by John Wheeler. Now, John Wheeler he studied under Bohr, and he actually had Feynman as his student. And he had this wonderful metaphor for how answers about reality can emerge from the questions that we ask in a way that is perfectly consistent and rule-bound and non-random without requiring any pre-existing truth about how things were. And this is how it goes. It's based on the game of 20 questions. So this game, I'm sure you all know, where where everyone chooses let's say, a person. Okay, one person goes out of the room and everyone else chooses a person, and then this one person has to come back in and find out who that person is by asking questions. And they have to be questions that only have a yes or no answer. Binary questions. As you can see, this is actually a quantum game. Okay, so let's say we play it like this. The person goes outside. We all decide on a person, we all do our thing, and then the person comes back in and starts asking questions. And on this occasion, the person who's come back in, she starts off in the normal way. She says, "Is this person alive or dead?" And is this person dead? And the answer is yes. Okay. Is this person male? Yes. Okay. And so it goes on, except that the questioner finds that as she asks more and more questions, it takes longer for the answer to come. The person she asks sort of has to think about it for a while before giving the answer, which is kind of odd because, surely it's either one thing or the other. Why do you have to think about it? Anyway, the game goes on, and eventually she thinks she's narrowing in on who it is, and eventually she says, "I know, it's Richard Feynman." And everyone says, "Yes, it's Richard Feynman." And everyone laughs, and the game is over. But then she says, "Well, what was going on? Why did it take you so long, each time when I was asking more and more questions to answer?" And everyone explains that they'd played the game a bit differently. They decided that they weren't going to decide on a person. They were simply going to make sure that whatever answer each individual gave when they were asked was consistent with all the other answers in applying at least to someone, ideally someone famous. So as soon as the first question, is this person dead, was answered yes, all the other people's answers had to be consistent with that. It had to be a dead person that they were thinking of. And then it had to be a dead male that they were thinking of, and so on. But the first person could just equally well have said no to that first question. And then they would have converged on someone else, not Richard Feynman. So the options become more and more constrained as the questions proceed, and it took longer and longer to figure out, who still is going to work, who's going to be consistent with all these answers so far. And everyone was forced by the nature of the questions to converge on the same person. If you had asked different questions, you'd have ended up with a different answer. So context mattered. There never was a preordained answer. You brought it into being, and in a way that was fully consistent with all the questions you'd asked. What's more, the very notion of there being an answer only makes sense when you play the game. It's meaningless to ask who the chosen person is in that situation without asking the questions about them. And quantum mechanics is a theory a bit like this, I think, of what is and what isn't knowable, and how those knowns are related and how they emerge from the questions we ask. And I like to think of this in terms of a distinction between a theory of isness and a theory of ifness. Quantum mechanics doesn't tell us how a thing is. It tells us what it could be, along with, and this is crucial, along with a logic of the relationships between those coulds and the probability that it could be this. So, if this, then that. And what this means is that to truly describe the features of quantum mechanics, as far as that's possible at the moment, I think we should replace all the conventional isms of quantum mechanics that I kind of started off with at the beginning with ifms. For example, we shouldn't say, here it is a particle. There, it is a wave. Rather, we should say, if we measure things like this, then the quantum object behaves in a manner that we associate with particles. But if we measure it like that, it behaves in a manner that is like a wave. We shouldn't say the particle is in two places at once. We should say, if we measure it, we will detect this state with probability x and this state with probability y. Now, this ifness is kind of perplexing because it's not what we've come to associate with science. We're used to science telling us how things are. And if there are ifs that arise, it's simply because we don't know enough. We're partially ignorant about those how things are. But in quantum mechanics, it seems like those ifs are fundamental. Well, okay, but what's the stuff that this ifness is all about? Quantum mechanics doesn't obviously tell us anything about that. And all we have right now are hints and guesses. And to try to bring them into sharper focus is a tricky business, which I think means we have to use sometimes an almost poetic level of expression, the kind of thing that will send a lot of physicists scurrying for cover. Take this attempt, for example, by the physicist Chris Fuchs. He says, perhaps the world is sensitive to our touch. It has a kind of zing that makes it fly off in ways that were not imaginable classically. The whole structure of quantum mechanics may be nothing more than the optimal method of reasoning and processing information in the light of such a fundamental, wonderful sensitivity. And what Fuchs means here is not the mundane truism that the human observer disturbs the world. Rather, he's saying quantum mechanics may be the machinery that we humans need at a scale pitched midway between the subatomic and the galactic to try to compile and quantify information about a world that has this incredibly sensitive character. So it embodies what we've learned about how to navigate in such a place. Well, at any rate, I think it's vital that we understand that this ifness doesn't imply that the world, our home, is holding anything back from us. It's just that classical physics has primed us to expect too much from it. We've just become accustomed to asking questions and getting answers, getting definite answers. What color is it? How heavy is it? How fast is it moving? Forgetting the almost ludicrous amount that we don't know about most things around us in detail, we figured that we could just go on forever, asking questions and being answered at ever smaller scales. And when we discovered that we can't, we felt shortchanged by nature, and we pronounced it weird. Well, that won't do anymore. Nature does its best, and we need to adjust our expectations. We need to go beyond weird. Thank you.